Welcome everybody. Our speaker is Elia Bruè from Bocconi University with a talk about Lyapunov Exponents and mixing in DiPerna-Lions.
Thank you very much, Camillo. Thank you very much to the organizers for inviting me. It's a great pleasure to be back in Princeton and have the opportunity to present my work. Today's talk is going to be about Bressan mixing conjecture. This is going to be the main focus. This is a conjecture by Bressan. He stated this conjecture in 2003. And today I want to present some new results based on tools from ergodic theory and dynamical systems. And then I'll try to make a connection with the theory of DiPerna-Lions flows, which is a theory initiated by DiPerna-Lions in 1989 and with second most important contribution by Ambrosio in 2004. And it is about flows of Sobolev and BV regular velocity fields. And I'll try to make a connection between the mixing conjecture, this non-smooth framework, and some extensions of classical tools from ergodic theory. Okay, so let's start with the conjecture. I'll present it in the smooth framework, exactly as stated in the original paper by Bressan in 2003. So I want to consider just a smooth time-dependent velocity field in the d-dimensional torus. The velocity field is assumed to be incompressible. And let's consider the flow map associated to it. Clearly, this is a well-defined smooth object in this framework, and it's going to be measure preserving. So the Lebesgue measure on the d-dimensional torus plays the role of the volume measure and is preserved by the flow thanks to the incompressibility condition. Okay, let's introduce a notion of geometric mixing. So the picture here is taken from the...
So the previous slide for a minute and going a bit quickly.
Sorry?
Can you show the previous slide?
Yes. Yeah, just a smooth time-dependent velocity field on the torus. All right. So this picture is taken from the paper by Bressan, where this conjecture is stated. And it says the following. So we have our flow map, and we divide the torus into two subsets. Literally, let's cut it in half. And we say that the map at time t mixes this subset A up to scale epsilon if you look at the image of this subset, which corresponds to this complicated picture over here. You take the intersection with any ball of radius epsilon, and you look at the volume. If the volume is between 1/5 and 4/5 of the volume of the ball, then we say that the set is epsilon mixed. Okay? So this is nothing but what is depicted over here. This is a typical ball of radius epsilon, and as you can see, it intersects certain percentage of the volume of the image of the set A through the map, and the same holds for the complement. Is this definition clear? Okay.
There's nothing magical about the fifth, is there? Or
no, it's nothing, of course. Yeah, thank you for asking this. 1/5, there's nothing special about 1/5. It's you can put there any constant kappa smaller than 1, and you're gonna have a notion depending on kappa. This is just my geometric parameters.
Okay, I never understood why not 1/3 and 2/3.
What you're not doing is asking that it's somehow close to the volume of A over the volume of the torus or something. It's just some amount. You're not asking that it actually evenly distribute, just that there's some everywhere.
Exactly.
Yes.
There's some everywhere. So, I
That'll
mean,
be important, I imagine, later, because usually people, when they say mixing, mean that, but you explicitly don't.
I don't. Okay. Then I'll also present another more classical notion of mixing. This is, I mean, I'm just introducing this because it's the original one appearing in the paper. But anyway, I think it will be slightly more clear in a second. But anyway, notion number one, geometric mixing according to this intersection with balls of a certain range.
Set A has measure half.
The set A has measured 1/2. Yes, the set A has measured 1/2. All right, conjecture. This is still open. Looks pretty innocent, but is, as far as I know, still open. Assume that your flow at time 1 mixes the subset A, this subset A, up to scale epsilon. Then the integral in time between 0 and 1 of the differential of the velocity field in L1 is bounded below by universal constant C, depending only on the dimension of the space, times log 1 over the mixing scale, 1 over epsilon. Of course, again, there's nothing special about time 1. You can, state this for every time and then simply rescale things. One interpretation of this is in terms of cost of rearrangement. So you have this configuration, which is somehow, not chaotic at all. And then you have an epsilon mixed configuration. And you try to map one onto the other by means of a flow map associated to a certain velocity field. This is going to cost something, and you measure the cost in terms of L1 norm of the gradients integrated with respect to time. And this cost is bounded below by the log of 1 over the mixing scale. And a possible heuristic here comes from a one-dimensional problem, which is solved in the 2003 paper by Bressan. So the title of the paper is A Lemma and a Conjecture. The lemma was about the rearrangement cost in the one-dimensional framework, and the conjecture is about the rearrangement in 2 dimensions. So exactly this conjecture. Is it clear so far? That's an open question. Let's try to make it, rephrase it in slightly different terms. First of all, there's nothing special about the initial configuration, 1/2 of the torus, 1/2 of the torus. One can consider more general initial densities. So we can pick any initial density rho, which is smooth, and say with 0 mean, we can always assume that the density is 0 mean. This is going to be convenient. You can think of this configuration as coming from the initial density +1 in the A region and -1 in the complement. Then, of course, you can evolve this in time. And when you evolve this in time, you're essentially solving the transport equation associated to the velocity field U with initial condition rho. Geometric mixing, you can, again, rephrase it in terms, you can rephrase it in this generality. So if you have an initial condition rho, then you get any 0 mean density rho xt. Then the smallest scale at which rho is geometrically mixed is going to be equal to this. You take the average in space of the density within a ball of radius r, and you consider scales above epsilon, or you consider the smallest parameter epsilon such that for all scales r bigger than epsilon, this average is below a certain threshold. So again, 3/5 in order to be consistent with the 1/5 I had before, but of course you can allow for any other parameter. So just to understand what is going on here, if we pick as initial condition rho the indicator function of the set A minus the indicator of the complement. So this is the function equal to +1 over A in the previous picture and -1 over the complement. Then, of course, when you evolve this in time, you get the indicator of the image of A and the indicator minus the indicator of the complement of the image. When you integrate this object over a ball of radius r, you get a difference between the amount of volume, the amount of volume, ball of radius r, intersection the set, and intersection the complement. And this requirement here literally amounts to what I asked in the second slide of this talk. It literally amounts to this.
I'm still puzzling about this 5. I mean, okay, so you can choose other numbers, but then the definition depends on those numbers. Is that right?
Sorry?
The definition then depends on.
Depends on this number. In principle, yes.
Some sense,
If you want, I mean, to be very precise, one would introduce a parameter kappa, say between 1, 0, and 1, and then call this number mix kappa, a mixing scale depending on the parameter kappa. This is, the standard terminology. Just to avoid, too many parameters floating around, I made the choice kappa equal 1 over 5.
Here you are considering every scale up to epsilon.
So epsilon is the smallest scale, such that the good, mixing property holds. Okay. So this mix rho is nothing but the smallest possible epsilon in the definition I had in the second slide.
Okay, because there is some hierarchy. If you mix at some scale, you mix at scales above. Because up to changing constant. There is
I mean, the picture to keep in mind, so something geometrically mixed at a certain scale epsilon is a chessboard with side epsilon, more or less. Of course, if you pick a ball which is 3 times the size, the ball is gonna still intersect as many black squares as white squares up to, some. Does it make sense so far? Okay. So, well, this is just a convenient way to rephrase Bressan conjecture. So again, this is the cost in Bressan conjecture, L1 norm of the differential of the velocity field, bounded from below by what? By the log of the inverse up to a normalizing constant, because now I'm not normalizing rho. Up to a normalizing constant is a log of the inverse of the mixing scale. Just a reformulation, okay? But what I like to think of this conjecture as some sort of universal bound on mixing efficiency. So if you simply, apply the exponential both sides, what you get is the following equivalent formulation. So the mixing scale of your passive scalar should be conjecturally always bigger than or equal of this negative exponential. So in other words, if you think of this as the mixing scale, which is the geometric mixing scale, or the degree of mixedness of our scalar, we know in general that scalars can be mixed exponentially by velocity fields. There are many examples, right? The conjecture says that, well, yes, you can mix a scalar exponentially, but never faster than a certain rate. And this rate is proportional to the L1 norm of the differential of the velocity field. Does it make sense? Okay. Cool. Now, I understand that this notion of geometric mixing is, a bit confusing, or at least not standard. Let's, maybe let's use some more popular notion of mixing in order to reformulate once more this conjecture. So typically in dynamical system, mathematical physics, one thinks of mixing in terms of decay of correlations, right? So we have a certain system, depending on time, discrete, continuous, doesn't matter. We pick two observables, rho and phi. Rho is the initial density, phi is an observable. Let's assume that they are both mean-free. And let's look at the correlation. So we integrate one against the other, we let time go, and we say that the system is mixing if in the limit t goes to infinity, the integral decorrelates, meaning that this converges to the integral of rho times the integral of phi, but since rho and phi are mean zero, it converges to zero. And you require this if you want some, notion of universal mixing. You ask this for every reasonable observable, say smooth zero mean. Okay, this is the classical notion of mixing decay correlations. Now, in this business, we want to quantify this, right? In order to quantify, we have to. It's kind of natural to take the supremum over all test functions phi appearing over here. So clearly, it's not a good idea to take the supremum when you take the supremum, you have to normalize in some space. And clearly, it's not a good idea to normalize in spaces like L2 or C0. Simply because the supremum over all phi in L2 gives the L2 norm of our scalar, which is constant. The problem is, you are not going to detect the decay of correlations if you take the supremum over L2 or C0 functions. Typically, in the dynamical system literature, people consider the supremum over Holder regular functions, and therefore the mixing is studied in terms of negative Holder norms of the scalar, right? In this business, people prefer to work with negative Sobolev norms for some reason. So this is a popular choice. So one takes the supremum over functions in H1, so the gradient of phi in L2 is normalized to be 1. And the functional mixing scale is going to be nothing but the H-1 norm of the density. Okay, that's the choice. It's pretty popular in the literature. And so one can again state the conjecture in terms of the functional mixing scale. So this is the degree of mixedness or the functional mixing scale, and it has to be bounded below in terms of the same exponential. So negative power of integral between 0 and t of the differential of u. So let me remark that this object is not equivalent to the geometric counterpart, but morally they are. I mean, in any possible partial result in this business, if you can prove something for the mixing, the geometric mixing scale, you're gonna be able to show something also for the functional and vice versa. But a priori, they are not the same object. Okay, so state of the art on this problem. So this is essentially to date the most important positive result is due to Camillo and Gianluca. They proved the following theorem. Bressan mixing conjecture holds provided you measure the cost in terms of the LP norm instead of L1 with P strictly bigger than 1, and the constant you get here does depend on P. And when P if you try to limit P to 1, this constant blows up. Okay. And you can, the main tool from analysis is the Hardy-Littlewood maximal function estimate, and this explains why you cannot reach P equal 1, and you can check that actually this extends very close to P equal 1. You can apply it on Hardy spaces. You can assume that the differential of the velocity field belongs to Hardy spaces or L log L type spaces, but you cannot quite reach P equal 1. And as I said, anytime you can show something in terms of the geometric mixing scale, there's, you can rephrase it also in terms of the functional scale, and this has been done by Ayer, Kiselev, and Xu. And it simply says that for every p bigger than 1, if you allow the constants capital C and small c appearing over here to depend also on p, you have the conjecture. You have the conjecture. Okay? Okay. Let me say something about other approaches very quickly. So there's one idea, this has been applied by many different authors, is to try to prove some propagation of regularity estimate for flows of smooth velocity fields and prove estimates depending only on the L1 norm or at least LP norm of the gradient of the velocity field. And it turns out that you cannot propagate strong norms such as Sobolev norms or Lipschitz norms if you wanna use only Sobolev norms of the velocity field to bound these terms. But a weak regularity function like this, which feels like a propagation of a log of the derivative. So this is a Fourier multiplier with a weight which is of Seitz log. Seems to be, at least when p is bigger than 1, there are results saying that you can propagate, you can estimate this object in terms of Sobolev norms of the velocity field. And the key point is that to do that, again, you need to rely on some tool from harmonic analysis. It can be Calderon-Zygmunt, it can be a maximal function estimate, but you always get the constraint p bigger than 1, exactly as in Camillo's and Gianluca's result. Those are the only two papers I'm aware of where something has been proven in the case p equal 1. In this first result, Yusman and Said prove a universal lower bound of mixing, but is not quite exponential, is tetration, which is like iterated exponential, so quite far from the Bressan mixing conjecture. And this is a result, a sharp result, so it's about exponential mixing, but within the class of alternating shear flows, which is a very particular class of vector fields. And already in this simplified toy framework, to get to the sharp mixing bound, it's very hard. Okay. Maybe just a few words about the main heuristic behind most of these approaches to prove the conjecture, at least when p is bigger than 1. So the key idea, the key principle, is a combination of propagation of regularity. Somehow the goal is to try to estimate some weak form of gradient growth in the systems with constants depending only on the relevant Sobolev norms of the velocity field. And then if you have good propagation of regularity, depending on the right constants, the idea is to apply just duality estimates. So mixing is about negative Sobolev norm. If you can bound the growth of positive Sobolev norm, then you rely on the fact that the L2 norm is preserved because of incompressibility, and therefore by duality you turn gradient growth into lower bound of mixing. This is somehow the general principle. So the key question then is what kind of regularity estimates I can get in this framework. So remember that here the velocity field is just smooth. So in principle, the flow is smooth, so there's, there are no strong constraints on the regularity, but the point is how you quantify the propagation of regularity. One naive attempt is to just apply Gromwald type estimates. So the, standard calculation standard estimate is something like this. You try to estimate how the distance between the two trajectories evolve in time. Just differentiate this, and you get the distance between the flow evaluated at the first flow line, the vector field evaluated along the first flow line minus the vector field evaluated at the second flow line. The typical thing you do when you try to show regularity for ODE type of systems. Then, in order to close ground wall, one would like to estimate this different quotient somehow, and typically you just use the Lipschitz constant of the velocity field. And then by ground wall, you realize that the growth of the Lipschitz constant of the flow is at most exponentially depending on this number over here. But this is exactly the estimate you don't want to run in this business, simply because you're going to end up on a mixing estimate depending on the L infinity norm of the gradient of U. But the conjecture is about L1 norm of the gradient, right? So the key striking idea in the paper by Camillo and Gianluca is to re-understand this calculation in the Sobolev fashion. So at this step over here, you don't want to apply the Lipschitz constant, but rather you apply the so-called Lewis-Lipschitz inequality. If I give you a Sobolev function, of course, you cannot, the function is not Lipschitz in general, but we should. You can estimate the difference quotient using, instead of a constant, a function. And what you need is the Hardy-Littlewood maximal function of the gradient of the velocity field at one point plus the same object at the second point. It's a pretty general fact for Sobolev functions. You don't have a Lipschitz bound, of course, but you can replace it with a bound depending on the maximal function of the gradient. If you do that, you end up with an inequality like this. In the classical ground wall, this is a constant. Here is a function. Is a maximal function of the differential, maximal function in space, integrated along the flow line. Now, in order to get something useful out of it, you need to control this function somewhere. The first thing to try is to bound this function in some LP space, right? And if you apply standard Hardy-Littlewood estimates on the maximal function, you realize that the LP norm of this function over here is bounded by the differential of U in LP, but you need P bigger than 1. Okay, so this is a weak form of regularity propagation, but is the key ingredient is enough to show a lower bound on mixing. This is the key technical point. Okay. Okay. So, what did we prove? We proved.
Sorry, Elia, could I ask a question?
Yeah, for sure.
So somehow, when you've got it down to this level, it feels like you can't do anything else. In the sense that, like, there's this step that you've made no assumptions in the velocity field, so you have to basically follow this path. And like this critical idea, of course, of kind of changing the Lipschitz to the max. So what are the other guys doing? Like,
I
mean, you showed us these other papers, but they seem to be somehow they're dodging this issue in some way. I mean,
so the other,
I don't see how you can improve on this argument.
No, the other approach is actually they don't improve, they essentially prove equivalent estimates. And one thing you can do is to simply differentiate in time this H log semi-norm. So at some point you figure out that this might be propagated, you differentiate in time and you try to estimate the derivative. What you get is a singular integral. And it turns out that the singular integral is bounded in LP, LQ spaces, and you close an estimate on this H log semi-norm in terms of the LP norm of the velocity field. And you discover
more sophisticated.
That's more sophisticated.
Just a more sophisticated max.
I mean, it's a different approach. It lands essentially on the same type of regularity. So actually weaker, to be very honest, because the other estimate, the one by Camillo and Gianluca, tells you that you have some weak differentiability, at least almost everywhere. Here you just get an H log propagation. But from the point of view of the Bressan mixing conjecture, you're going to get the same exact conclusion. Another approach has been more Eulerian in nature. So you look at the transport equation, you study a commutator. This idea comes from the DiPerna-Lions theory, and you try to make very quantitative estimates on the commutator and turn them into regularity estimate. And again, you get a propagation of the log of the derivative. And I will say those are all general ideas on how to get some regularity in this setting. And you can turn, this is another remark, you can turn this Lagrangian estimate into a bound on the H log norm. So you realize that this implies a bound on the H log norm, but it never implies any stronger bound, any fractional or integer Sobolev bound on the scalar or on the velocity field. Okay, cool. So what did we prove? So again, same framework, but now we assume time periodicity. So we want to play some periodicity game. So the velocity field is time periodic, and therefore you can think of this dynamic as a discrete dynamic. We are just iterating the flow map at n1. Okay. Let's look at the top Lyapunov exponents. Of course, in this framework, one can define all the Lyapunov exponents, but in the following statements, only the biggest Lyapunov exponent is going to play a role. So this is nothing but the limit 1 over t log of the differential, and it measures the exponential expansion of the gradient point by point. So here is the statement we have. Just, I mean, a small technical point here. I'm looking at the row composition, the flow instead of the inverse. It doesn't play any role. I mean, it's morally the very same statement. Just to avoid the ugly notations defining the Lyapunov exponent backward in time, but it's totally irrelevant. So here is the statement. We can think of it as a lower bound on the top maximal exponent, actually a lower bound on the average of the top Lyapunov exponent. So the integral of the top Lyapunov exponent up to a constant which is universal, it depends just on the dimension and the initial condition at most. We can bound this below in terms of this asymptotic quantity. So we look again at the inverse of the mixing scale, now the functional mixing, but we have the very same statement for the geometric mixing. We take the log, so this is exactly the quantity appearing in the Bressan conjecture, but we divide by time and we take the limit. So as I said, this is, you can think of it as a lower bound on the average of the top Lyapunov exponents, and one can think of it as a refinement of an estimate which appeared in the recent paper by Dolgopiat, Kanigovsky, and Rodriguez, where they studied discrete dynamical systems that are universally mixing, and they proved that they are Bernoulli. And one of the steps in their proof is to show that universal mixing implies positive Lyapunov exponents, so that they could apply some tools from Pessin theory. Yeah.
Does universal mixing mean?
You mix exponentially all the initial conditions with a reasonable regularity. Say all H1 initial conditions are mixed exponentially by your dynamical discrete dynamical system.
Does that definition comes with some uniformity on the estimates, or
with a uniformity on
with some uniformity on
so
the
you fix a parameter beta, you drive in the exponential mixing, and you assume that the h-1 norm of whatever initial condition you pick, composition, the map, you take, you iterate, and this is gonna go down like e to the minus t beta, e to the minus beta n, where beta is the rate and n is the number of iterations. And here there's nothing, I mean, our result is not about universal mixing, so it's you give me a flow and you give me one row and you always have this inequality. So the universal mixing is about this paper, okay? But I mean, in terms of Bressan, you can think of this as a bound on mixing efficiency, at least at the asymptotic level. So if you know that asymptotically your initial condition rho gets mixed at an exponential rate with parameter beta, so if you know this exponentially, then this estimate is telling you that beta cannot be too big. Beta needs to be bounded by the average in space of the top Lyapunov exponent. So if you want, is a bound on mixing efficiency in terms of the average of the top Lyapunov exponents instead of the quantity appearing in Bressan mixing conjecture. Does it make sense? Okay, so morally speaking, this is not surprising at all. The object appearing over here, it measures the gradient growth, the exponential gradient growth, right? So I'm just saying that if you want to mix by duality, you never mix faster than the exponential gradient growth you might get. Okay, but the key point is that you want to make this very precise in terms of the right norm on the Lyapunov exponent. And this is because the right norm on the Lyapunov exponent allows you to bound this term in terms of the one appearing in the Bressan mixing conjecture. This is a pretty soft estimate. I'll show you why it's true, but it's really, the elementary thing. This number is always smaller than the differential of u in L1, exactly as conjectured by Bressan. And so in particular, if you collect this observation and the main statement, you deduce an asymptotic version of Bressan conjecture. So if I'm allowed to wait long enough, and I cannot quantify this star, then I can lower bound with the right quantity the exponential mixing. This is more or less the message. And the moral again is that standard harmonic analysis tools essentially cannot apply to the case p equal 1. They stop at p bigger than 1. So here we are using some new ingredient based on ergodic type arguments, and we are able to go beyond to reach p equal 1, but we pay a price. So this holds only asymptotically.
Is it so important that your thing is time periodic?
Not, it depends. For this estimate, no. For this, yes. If you want to show directly this without, passing from Lyapunov exponents, you can do it there's a trick to do it, and you can relax the assumption on periodicity. But otherwise, it's not even clear that you have a top Lyapunov exponent. So you have to add assumptions on ergodicity of the time periodic vector field and so on in order to have.
But so you need some assumptions on you cannot take.
No, if you want to show, if you want to, relate.
No, the other bound, the asymptotic bound.
This asymptotic bound, if the vector field is smooth, time dependent, I can prove this one without passing for the top Lyapunov exponent estimate.
So you just need the smoothness.
Just need the smoothness. Actually, I just need some C1 plus epsilon Holder regularity. I need something above the C1 bound. Uniform in time. Uniform in time. Yeah. So, okay, so this is the model, and the other point is that...
But then you don't derive it as a corollary? So now I'm confused. Because you say you need the time periodicity to derive the other one, or is anyway using the other estimate in some way?
So no, what I'm saying is that to derive the sharp thing, which is this, I need time periodicity.
Right.
Because I cannot even define, or I mean, assumptions that allow me to define the top Lyapunov exponent.
Yeah, that I understand. But then if you are able to get this other estimate without the optimal thing, it means it's not only provable as a corollary, or am I?
It's not. I mean, it's not. If you give me a uniform regularity bound on some higher regularity norm like C1 epsilon, I can prove it with a different argument.
So it's a different argument.
It's a different argument.
Okay.
Totally Lagrangian, which does not pass through the ergodic theoretic machinery. Okay. And and another conclusion is that, well, if you look for a counterexample to Bressan, you should be able to get some anomalously fast mixing, but in short time, because you know that after a while you're gonna be in a regime where the conjecture is essentially verified. Okay. So this is just about this bound over here, and as I said, it's very elementary. It just comes from the by integrating the ODE, evolving the differential of the flow. So the differential of the flow evolves according to this linear ODE. So 1/t log of the differential evolves according to this, and now it's pretty clear that if you integrate both sides, pass to the limit, you end up with what you expect. Okay. And I mean, this inequality is generally strict. I mean, most of the systems have 0 Lyapunov exponents. There's no exponential growth at all, but this integral over here, it's, in any non-trivial system is positive. Okay.
Here is where you're using time periodicity.
Exactly. This is one of the points where I'm using time periodicity. Now, let's make a connection with the non-smooth framework of DiPerna-Lions flow. So the conjecture, Bressan mixing conjecture is about smooth vector fields, but it's actually intrinsically not smooth. So it's about estimating things in terms of Sobolev norms only, right? It's kind of natural to phrase this in the framework of flows and velocity fields that are Sobolev regular. And also when it comes to regularity questions, it's very hard to figure out whether a certain estimate can be done in terms of constants depending only on the Sobolev norm of the velocity field when the velocity field itself is smooth. It's much easier to work directly at the level of Sobolev velocity field. If you have a certain estimate depending on the Sobolev norm, well, you get it. If not, it's very, very likely that you're going to find a counterexample where the quantity you want to estimate is just plus infinity. And just, I mean, analogies, if you're interested in smooth functions, but the key energy is the Dirichlet energy, of course, it's much better to look at Sobolev functions. And in more geometric terms, if you're interested to manifolds with lower bound on the curvature, say sectional lower bounds, and this is the only a priori geometric bound you have, then probably it's much better to look at Alexandrov spaces that are the non-smooth counterpart of manifolds with ornate sectional curvature. And in this framework, in the context of Bressan mixing conjecture, the natural framework is the DiPerna-Lions framework, which is about flows of velocity field satisfying the W1P regularity in space with P bigger than or equal to 1. And actually this theory is much older than Bressan conjecture. It has been initiated by DiPerna-Lions in 1989, Ambrosio in 2004. And there are lot of motivations to study flows in this framework. So they mainly come from PD. In fluid dynamics, for instance, it's plenty of models where you have a priori Sobolev controls on the relevant velocity fields, but nothing better. But even in geometry, this is kind of an interesting framework. So if you study spaces with a lower bound on the Ricci curvature, typically, and if you look at flow of geodesics, typically you can bound the relevant velocity fields in W12. You can bound Hessians in L2, but you never do better than this. So there are several different frameworks where you would be interested in dealing with flows of Sobolev regular velocity fields beyond the Bressan mixing conjecture. Now, question number 0. Do we have a flow? So a priori, you cannot hope for uniqueness of trajectories. If you pick a point, you may have infinitely many trajectories coming out of a single point. The key principle in this theory is that there's a way to define a notion of generalized flow. And the idea is to look at all possible trajectories starting from all possible points, but then at a given point, at every point, you make a selection argument. So you select one trajectory for every point in such a way that the bundle you get, the flow you get out of this selection satisfies a global property. And the global property is the Liouville property. So you impose the Liouville property as a selection principle to get something meaningful out of uncountably many possibilities. So to be very precise, in the original formulation, you don't use incompressible velocity field. You can work with velocity field with bounded divergence, and you relax accordingly this requirement. But in our incompressible framework, this is going to be totally equivalent. So the first principle is that in order to define a good notion of flow, you use the Liouville property as a selection principle. And it turns out, this is a deep theorem by DiPerna-Lions and Ambrosio, that there's a unique flow satisfying this property. And this is called the regular Lagrangian flow. It's unique, it's stable, it satisfies a set of good properties. And also it turns out that if you study the problem from the Eulerian point of view, so you look at the transport equation, you can always make sense of this in the distributional formulation. You need very little. So in particular, when the density is bounded, this makes perfect sense. And it turns out that this problem is well posed. You fix density and you get a unique solution in the class of bounded densities. And more than this, the density is transported by the regular Lagrangian flow, the good object you get out of the selection principle. Okay, so those are the fundamental facts of this DiPerna-Lions theory. From the quantitative side, you have the same estimates I showed you in the sketch of proof for Bressan conjecture when P is bigger than 1. They are due to Camillo and Gianluca. And essentially, you can apply this sort of argument directly in the non-smooth setting. And you deduce that, among other things, you deduce that the flow, which is not smooth in general, is at least approximate differentiable, which is a slightly weaker notion than differentiable almost everywhere. And you can bound, you have the quantitative bound on this approximate differential in terms of the function appearing over here, which again depends on the differential of the vector field. And actually, this approximate differentiability upgrades to classical differentiability almost everywhere as soon as P is bigger than D, but this assumption is necessary. And also, you can try to figure out whether one has stronger regularity estimates on the flow and on solution to the transport equations, and it turns out that you don't. It is possible to construct examples of flows and solution to the transport equations such that any Sobolev even fractional regularity is lost as soon as t is positive. The best you can bound is the h log derivative, a functional like the one I showed you at the beginning of this talk. And an open question, which is pretty much related to Bressan mixing conjecture, is about propagation of regularity in W11 or B. As far as I know, there's no positive result in this direction. Literally no norm stronger than the L2 norm is known to be propagated in this case. You can get something very implicit by compactness, but I'm not aware of any stronger regularity result than this. An interesting thing is a notion from this work by Lyapunov of differential in measure. So it turns out that you have enough regularity to study this problem. So du is an LP function, and therefore you can study this linear evolution problem, and is well posed. And you can show that the difference quotient minus the solution to this problem over here converges to zero in some sense. So you have some sort of very weak notion of differentiability, but it does only measure. A function W satisfying this property is called the differential in measure, and you can prove that this notion is even weaker than approximate differentiability. And it turns out that when p is bigger than 1, this W coincides exactly with the approximate differentiability you can get out of the Kripa-Delius estimate. Now, an interesting fact is that in the periodic framework, you can use this W as a cocycle, and you can apply Oceledet theorem. And so it turns out that you have a well-defined notion of Lyapunov exponents in this very non-smooth framework. And this is true for every p, even p equal 1. Important fact, when p is bigger than 1, this W coincides with the approximate differentiability, and so you have a notion which is slightly more meaningful, because the approximate differentiability relates better to the flow itself. While
so could you clarify? So here is the core piece over here basically the classical Oceledet theorem?
That's just the classical
Oceledet theorem. You're just saying that for our lefts, Oceledet theorem holds.
Exactly. Okay. This is just the classical Oceledet theorem, and you can apply it using this cocycle W.
Sure.
It behaves as a cocycle. In the smooth framework, this W is just the classical differential, and you get classical Lyapunov exponents.
Okay.
In the intermediate framework, p bigger than 1, this W is the approximate differentiability, and you get Lyapunov exponents depending on the approximate differentiability. In full generality within this theory, this W is just the differential measure, and you get numbers depending on this differential measure. And what we managed to show is the very same theorem in the non-smooth setting. So what we proved in the smooth setting actually holds in the DiPerna-Lions framework with a big assumption, p bigger than 1. It's literally the same statement. So if you want, this is telling us that the time t star appearing over here does not really depend on higher derivatives of the velocity field, but it might depend at least on LP norm p bigger than 1 of the differential view. Okay. So the case p equal 1 remains open, and there are two main obstructions. The first obstruction is that differentiability measure is a very, very weak notion. So even though you have these numbers coming out of differentiability measure, it's not clear how to use them to prove anything useful. And the second point is that you cannot rely on any stronger notion of differentiability, even if you want to use it, you want to use this notion in a qualitative way in your argument, you simply can't. There are no differentiability results available in the case p equal 1. But then at this point, we asked a very natural question. So we have these numbers that one can define in this very no-smooth framework, but what can we prove besides bounds on mixing using these numbers? And actually, we realized that it is possible to show, this is somehow surprising, maybe, is it possible to reprove Ruelle inequality in this framework? So Ruelle inequality is a bound on the metric entropy of the system in terms of the integral of positive Lyapunov exponents. So typically this result in the dynamical system literature is stated for maps or flow maps satisfying C1 plus C1 regularity. And there are counterexamples below C1. So here we are getting the results for flow maps of Sobolev velocity fields that are not even fractional Sobolev regular. The key point is the approximate differentiability coming out of Camillo and Gianluca's estimate. So in other words, what we are proving is that if you give me a map satisfying an estimate like this with a function g in LP, this map is not gonna be Sobolev, even fractional, but it will be enough to prove a bound on the entropy in terms of the Lyapunov exponents, as in Ruelle inequality. And this generalizes, our framework generalizes classical results like Katok, Strelchin, Ladrapier, Pritsky about bounds on entropy, Ruelle inequality in the class, in certain class of singular maps that occur in certain applications of dynamical system. Okay, let me just mention one final question. In the case p equal 1, which is the relevant case for Bressan mixing conjecture, we can define Lyapunov exponents, as I said. Of course, you can define the metric entropy, so the metric entropy is always definable as soon as you have a map, but we don't even know whether the metric entropy is finite. So as soon as p bigger than 1, we have a very precise bound, the one given by Ruelle. When p is equal to 1, we cannot even show that this number is finite. And this question really feels like Bressan mixing conjecture or some propagation of regularity, some weak form of propagation of regularity. And yeah, I'll stop here. Thank you very much for your attention.
Okay, great. Thank you very much. We have other questions.
So my question was exactly what you put on the board in the last slide. But so if you take the asymptotic version of this, it's you know how to do this?
What do you mean this one?
Bound the entropy is kind of asymptotic growth of entropy.
If the vector field is just W11, I don't. Again, the problem is that we have some asymptotic information coming out of Oseledet, but this differential measure is very weak, and we don't know how to use it.
But if it was smooth, then this would be easy.
Yeah, then yes. Even W1P with P bigger than 1, it works. The tough problem is the case p equal 1.
Other questions? Okay, we can take
Yeah, actually, so yeah. So here you're not assuming time periodicity.
Yes, I am.
Or are you? You
I
are.
am.
Okay, it's there. Okay, so that's one period. Yeah, yes. And I mean, somehow the higher regularity doesn't. I mean, because in the other case you said if I am.
Yeah, I mean, you cannot, I mean, if you put
something, I would be able to leverage it. But so here the W1P isn't helping.
If you, instead of looking for a very precise bound in terms of Lyapunov exponents, here you pay something, some constant depending on the LP norm of the vector, then it works.
So you would be able to prove it's finite.
Yes.
Okay.
Yeah. If your goal is to show that it's just finite, yes, you can drop the periodicity assumption. You need some extra regularity assumption, uniform time, and then it would work.
But with the one periodicity, even I mean W11, you're not able to do even with the one periodicity.
Yeah, it's not a matter of periodicity; it's really the
It's
lack
really
of regularity. Lack of regularity and lack of somehow. I mean, it's very hard to get any quantitative information
from that guy
out of this very weak differentiability, this convergence in measure of the difference quotient. Yes, that's the point.
It's like getting some information from weekend one. Sounds like similar.
Yeah, but you never reintegrate such an information. Yeah, I mean, the state of the art is very easy to state. When P is equal 1, there's no regularity results whatsoever for the differential, for the flow of a W11 velocity field. So any energy function you might come up with which measures some degree of regularity, I wouldn't know to show that it's bounded. Any rate, any Fourier multiplier, whatever. And in particular, we cannot even bound the entropy, which is a different object. I mean, it's not really about regularity. It's something else. But typically, when you estimate the entropy, you need to use some, regularity control on the dynamic or something.
Okay, so thank you very much, Elia.